Is this a laser? Great. All right, thanks so much for having me. So my name is Tej, and I'll be talking today about flow-based generative models that we're using, also known as bijective generative models, in application to lattice field theory. So this is work in collaboration with Michael Albergo and Fiala Shanahan, who actually presented earlier today. And you can find more information in this work that's up on the archive right now. So let me begin by talking about the general setup of our problem. So what is lattice field theory, and why is this a hard problem, and why is ML potentially useful for us? So this lattice field theory is a tool to access quantum field theories in general. And these are particularly interesting because they seem to work very well to describe our world at the smallest scales. So we actually had a few talks earlier today on the collider experiments and the detectors that are placed at the Large Hadron Collider. And these observe to very high accuracy the processes that we expect from quantum field theories. And we would like to make better and more accurate predictions based on our theoretical understanding of quantum field theories. And yet we run into limitations, in particular when we look at the strongly coupled components within quantum field theories. So for example, the strong force that binds protons and neutrons together and binds these into nuclei. So one particular approach to access this is a computational approach, is lattice field theory. And in lattice field theory, we proceed by discretizing our space and time and setting up essentially a statistical problem. So in the case of the strong force, we look at the particles known as gluons and quarks, and these are represented by particular values on this space-time lattice, where the values that we write down on this lattice are distributed according to a particular distribution. This is written down in the bottom left corner, where that distribution comes from the framework of quantum field theory and is sort of handed to us in a very precise way by how the quantum field theory should operate. So rather than talk about this strong force quantum setup for the strong force, for gluons and quarks in detail, I'm going to look in particular at a toy model for the remainder of this talk. So I'll mention that in just a sec. But I want to highlight one of the particular problems we run into when we try to actually calculate physics from this statistical setup. And that is that to draw samples according to this distribution, which would give us answers to the physics questions that we care about, we run into a prohibitively expensive scaling as we try to go closer and closer to the physical parameters that we care about. And this is known as critical slowing down, and Fiala mentioned it in our talk earlier today. So let me now simplify to a particular toy model, the scalar lattice field theory. This is just a sort of sketch of what the more complex setup is in the strong force calculations that we care about, but is a particularly useful one because it highlights the problems that we do run into in that case. So in this simplified model, we have one real number on every side of a lattice. And so you can sort of think of this as analogous to a one-channel image. The only difference being that this is a real number, so it's continuous and goes from minus infinity to plus infinity. But other than that, if I plot out samples from a particular set of parameters in this theory, I get things that look like images. And importantly, the physics tells me that the images have these particular features in them. They have correlations on a scale that's defined by the parameters of the theory. And you can see these sort of blobs of correlated values, light and dark, representing more positive and more negative values here. So in any sort of generation of samples from our desired distribution, we should reproduce these features. And in particular, we should be able to get more likely field configurations more often, and the less likely field configurations according to our distribution far less often. And this has to happen according to exactly the right proportions of weights prescribed to us by quantum field theory in order to truly reproduce the physics that we're trying to get at. So we need to be exact about this. But otherwise, this problem looks very similar to the problem of generating images. So on the image generation side, let's say I wanted to draw images that looked like cats and dogs. Well, I would want it to be very likely that I pull out images that look like the top two on this right-hand side, and fairly unlikely to pull out this very noisy looking image at the bottom that's in fact totally uncorrelated pixel to pixel. So there are some similarities here with the image generation problem, but let me just highlight some of the differences as well. And some of these differences help us in the problem, and some of these differences actually hurt us. So a helpful difference here being we have an analytic hold on what the distribution is that we want at the end of the day. This is the e to the minus s that I highlighted in that earlier slide. And so we can, given a sample, calculate exactly what the relative probability should be. So I note that this is up to normalization. We don't get the exact probability density, but we do, given two lattice samples, have the ability to compare how much more likely should I be to draw one over the other. There are also many symmetries that come from the physics. So in particular, we're putting this on the lattice. So there's translation, rotation, and reflection symmetries. And that is reflected in the distribution. So if I take a particular lattice and a lattice configuration and I rotate it, the probability of drawing that rotated configuration should be exactly the same as the unrotated configuration. And so in any sort of generative setup, we might exploit some of these symmetries to reduce the number of parameters that we actually have to train at the end of the day. There are similar internal symmetries that have to do with updating the values on the lattice sites as well. On the negative side, we're looking at theories that have many variables in our sort of target theories of interest. So this was mentioned earlier today, but it would be ideal to try and target lattices that have 10 to the 12 or order 10 to the 12 variables per configuration. And this is a very large scale problem that would make training difficult and also makes sort of the practical implementation sort of difficult at the end of the day. And finally, because of this problem of critical slowing down, once we get towards physical looking parameters, we run into the issue of actually generating our training data if we're to use any sort of a machine learning approach to this problem. So we, in general, could only manage to produce, with reasonable practicality, order thousands of samples from the distribution, which is much fewer than the number of variables that we're hoping to sort of train this distribution over at the end of the day. So I'll now discuss the approach that we're taking that exploits some of the positive aspects that I just mentioned and hopefully avoids the pitfalls associated with the negative aspects. So we, in this work with Fiala and Michael, have been looking at flow-based generative models. So these are models, also known as normalizing flows or bijective flows, that use an easily sampled prior distribution, draws from that distribution, and maps through an invertible function to produce samples from a new distribution via this change of variables that you hope and you train to approximate your distribution of interest. So the sampling procedure in this sort of a setup would look like draw a batch from this easy distribution, map through a parameterized function, and then you have your samples at the end of the day. On the other hand, if you would like to perform inference, you can map backwards through this map from any given sample to look at the density associated in your prior distribution as well as the Jacobian from the change of variables to give you the overall density of having drawn that sample. And altogether, this gives us a nice framework for sampling in a way that we can compare the sample density against the known analytic density that we would like to produce at the end of the day. So in our particular work, we focused on a real NVP, or real non-volume preserving construction of these normalizing flows. And the reason for that is it's been applied fairly successfully in the case of image generation. And so this sort of a setup works by dividing this flow into, or dividing this map into the composition of several smaller, very simple maps. One of these maps looks like an affine layer, so it looks like a transformation that scales and translates or shifts, where the scaling factor and the shift factor are themselves neural networks. And the reason we can do this and still have an invertible transformation is we choose to split the input variables into two halves. Here you have a green half and a black half. We only update one of the halves, and we only use the unupdated half as the input to the neural networks. So while the neural networks might be arbitrarily expressive and complicated, they are still defining an invertible map because the resulting half that they take as inputs sticks around after the transformation. So at the end of the day, we have something with a nice simple inverse and a tractable Jacobian, so we can have a well-defined normalizing flow models. And if we now go to train, what we have to do is backpropagate through these sorts of networks through all of our layers and update the parameters to come up with a distribution at the end of the day that hopefully looks very close to this distribution of interest. So that training, we in particular have chosen a shifted KL divergence, and the reason for this is to make use of our analytically known distribution, which is defined in terms of this S, which if you recall back to this formula here, defines our density associated with any particular sample, any particular lattice. And we've chosen a KL distribution because by this asymmetry, we can exploit the fact that this can be defined or estimated in terms of sampling with respect to only the model distribution. So let me just briefly touch upon the fact that we can make this exact by putting it in the Markov chain Monte Carlo framework. And the way we do that is by using these sorts of models as a proposal step in a Metropolis Hastings. This is a well-known Markov chain step that's been used in these sorts of physics applications before. But here we employ a machine-learned technique that can then be plugged in and made exact in a very precise way, such that we get the right distribution out, regardless of how correct or incorrect the distribution is. The difference between a very well-trained model and a poorly trained model is only in this acceptance rate, which has to do with the efficiency then of your Markov chain and how quickly you get decorrelated samples. So I've just schematically sketched this down here, but each of these proposals down at the bottom would be drawn from the model, while the chain would be updated in each of these steps by an acceptance or rejectance of the proposal according to the Metropolis Hastings algorithm. So we implemented this, and we tried it out on this toy model that I was talking about, the scalar lattice field theory. And we in particular focused on two-dimensional lattices of sizes on the sort of smaller side for this proof of principle, ranging from 6 squared to 14 squared lattices. And the idea here being, with this range of sizes, we could investigate this critical slowing down. We could tune the parameters as we get to larger and larger lattices to keep the physics the same, but approach this sort of physical limit of our discretization becoming smaller and smaller. And this is where usual updating algorithms would run into difficulty, but as I'll show in just a second, we avoided such difficulties with this sort of a setup. So the model itself used a variety of a range of parameters, varying between 8 and 12 of these layers making up the normalizing flow. There was this checkerboard pattern. There was a variety of different choices that we made depending on the scale of the lattice, between 2 to 6 fully connected layers, 100 to 1024 hidden units. And these were just sort of arbitrary choices we made for this proof of principle. I mean, one could have tweaked these and still gotten similar results. The point that we were attempting to make with this initial work is that this does work to produce lattices, and that you can, in fact, get a reasonable acceptance rate within this Markov chain making things exact. So finally, I should just mention, we did train to achieve a fixed acceptance rate. So that was our criterion for stopping training. And the acceptance rate, if it had reached 100, would have indicated that our model was, in fact, drawing exactly the right distribution. So we didn't go to the exact correct distribution, but by implementing this Markov chain, still got exactness in terms of the physics at the end of the day. So here's just sort of a sketch of the results. If you look at the 5 different sizes, you can see the top row is some samples drawn from the ML models, and the bottom 2 are from standard Markov chain methods. And just by eye, they sort of look varied. They have correlations on the right scales. If I go to the actual physics results, these are just 2 observables that we looked at. You can compare them across all of our lattices, and the black and the pink, indicate the standard methods, while the blue indicates our ML-generated methods. And things compare favorably within error bars. So as expected, the Markov chain does make things exact. And by by training to a fixed acceptance rate, we managed to get reasonably efficient statistics out of our machine learned models. So the final sort of question was, does this address the problem of critical slowing down? And you can see this problem highlighted on the left 2 plots here in the 2 standard algorithms that we compared against. As I scale my lattice to larger and larger sizes while trying to keep my physics fixed, this tau int, which is an autocorrelation time, or which is really a measure of cost, does increase exponentially. On the other hand, for my machine learned models, I've plotted out here 2 different sets of models. One trains to this 50% acceptance mark, and one trains to the better 70% acceptance. And you'll notice that in each case, there's sort of a flat line across going to larger and larger lattices. And while training to a higher acceptance rate does improve overall my efficiency because my cost per decorrelated sample goes down, in either case, I've removed sort of the critical slowing down problem that we face in the usual simulation strategies. Now, there's a caveat here, of course. This isn't for free. We've paid for this upfront by doing a training step where we actually tried to train and get the model distribution to match our true distribution. But by moving this cost up front, you can sort of pay for it once and then get decorrelated samples continually from there on out. And so this is perhaps a better formulation of the problem, and one that also we could apply more standard machine learning training methods to. So the final sort of note here is that there are many generalizations that we hope to attack. So we would like to go to higher space-time dimensions. We've only worked with 2D lattices. Our ultimate dimensionality, of course, that we'd like to go to is 3 spatial dimensions in 1 time, as we see in real life. So we would need to increase that. We'd also, of course, need to scale this method. So we've worked on small lattices for now. The question being, how does this scale up? What techniques do we have to apply to make it scale well? And finally, this was a very simple theory. So we are targeting eventually some more complicated theories and might need to develop some additional machinery to get there. So with that, I think I'll leave it off. Thanks for your time.